Welcome to this presentation by Professor Gottapu Sasibhushan Rao, Senior Professor, Department of ECE, Andhra University College of Engineering. In this video, we explain how the Kalman filter is used for GPS position determination, that is, for solving the GPS navigation problem. In GPS, the receiver determines its position from satellite pseudorange measurements. Since the range equation is nonlinear, it is first linearized. The Kalman filter then combines the current measurements with the previous position estimate to obtain a smoother and more reliable solution. We begin with a basic pseudorange equation for each satellite. It relates the measured pseudorange to the satellite position, receiver clock bias, and measurement noise. Since this equation is nonlinear, it must be linearized before applying the Kalman filter. First, an approximate receiver position and clock bias are selected. This initial estimate may come from a previous solution, a coarse position fix, or a least squares solution. Using this estimate, the predicted range and predicted pseudorange are calculated for each satellite. Next, the residual pseudorange is obtained by subtracting the predicted pseudorange from the measured pseudorange. The unknown correction state contains corrections to the receiver's X, Y, and Z coordinates, together with the receiver clock bias correction. The nonlinear range equation is linearized using a first-order Taylor series expansion. This gives the linear observation model. The geometry matrix, H, represents the relationship between changes in receiver position and the corresponding changes in pseudorange. The main difference between the Kalman filter and least squares is the use of a state evolution model. Before processing new measurements, the Kalman filter predicts the current state from the previous state. It also predicts the corresponding error covariance. The innovation is the difference between the actual measurement residual and its predicted value. It indicates how much new information is present in the current measurement. The Kalman gain then determines the appropriate balance between the predicted state and the new GPS measurements. The predicted state is corrected using the Kalman gain and the innovation. This produces the updated estimates of receiver position and clock bias corrections. The covariance matrix is also updated to represent the uncertainty remaining after the measurement update. Finally, the estimated corrections are applied to obtain the improved receiver position and clock bias. This updated solution becomes the starting point for the next measurement epoch. The predict and update process continues recursively, making the Kalman filter well suited for real-time GPS tracking.